All right, so this is 4.8 part 4. This should be the last portion of this section. And we're starting at example number 7, continued, which is on page number 9 of this unit. So it says solve the initial value problem. They give you the derivative. We have information that y at 1 equals 0. So once again, if you want to have the original function, I have to integrate the derivative. So if I look at this, 1 over 1 plus x squared, that's a quotient, but I have a rule for that. So the rule states that if I integrate 1 over 1 plus x squared dx, that equals inverse tangent of x plus c. So I'm going to use that rule here. So I'm going to integrate the derivative, which is 1 over 1 plus x squared dx, which we just discussed equals the inverse tangent of x plus c. Now I have to solve for c. So my function currently gives me a whole bunch of values because I have inverse tangent of x plus c. So second step is to find c. So how do I find c? I use the information given. I know that y equals 0 when x equals 1. So I'm going to plug that into that formula. So I get 1 equals inverse tangent of x, which is 1, plus c. And I'm solving for c. So I know the angle that matches up with inverse tangent of 1 is pi over 4. So I get, and by the way, y is 0, so not 1, but it's 0. So let me fix that really quick. So my equation says 0 equals pi over 4 plus c. Now I'm going to take pi over 4 and move it to the other side, and that's going to be my c value. So my third step is to write my function. So y equals inverse tangent at x plus, or minus in this case, negative pi over 4. Okay, so once again, these problems are asking you to find the initial value problem. Okay, so on the bottom of page 9, there's example number 8, which says solve the initial value problem for the derivative x, which equals, the second derivative of x, which equals 6 times e to the 2x plus 1. And then it gives us 2 bits of information. It tells us that the first derivative at 0, when x equals 0 equals 5. And then the second derivative, the original function at 0 equals 1. So for this one, we notice that we're given the second derivative. So basically what we have to do is double integration. So when you're given the second derivative, you have to integrate the second derivative, the first derivative, to get back to the original function. Okay? So first steps first, we're going to integrate that second derivative first. Okay, so the second derivative was given as 6, and I'm going to pop that out because it's a coefficient, e to the 2x plus the integration of 1. And these are in terms of x. Okay, so remember we have a rule. The rule says if I integrate e to the kx dx, that's going to equal e to the kx over k plus c. Okay, so this first one is going to be 6 times e to the 2x over 2. And the integration of 1, that is rule 1. So rule 1 says integration of 1 dx equals x plus c. So I get x here plus c. Okay? All right. So my next step is I have to find out what c is for the first derivative. So let me rewrite this. So y equals 2 goes into 6 3 times. So 3e to the 2x plus x plus c. Remember that this is the first derivative. Okay, because I just integrated one time, okay? All right, so the information that I know right at this moment is that at the first derivative, when x equals 0, y equals 5. Okay, so x equals 0, y equals 5. I'm going to plug these values in to find c. So I'm going to find c. Okay, so the first derivative's value was 5 for y, and then all of my x values are 0. Okay, so this becomes 5. On this side, it becomes 3. E to the 0, anything raised to 0 power is 1. So I get 5 equals 3 plus c. Okay, c therefore equals 2. Okay, so now that I have that, I can write my formula for the first derivative as 3 e to the 2x plus x plus 2. Okay, so if I want to get back to the original function, my next step is we have to integrate, and I don't know why this pen is acting up, so give me a second here just to rewrite this. So the next step is to integrate the first derivative, and that will give us the original function at x. Okay, so let's go ahead and do that. I'm going to integrate 3e to the 2x plus x plus 2 dx. Okay, so once again, we're going to use that rule that says e to the kx. If I integrate that, I get e to the kx over k. So this first one is going to become 3 e to the 2x over 2. And then if I integrate x, remember I have to use rule number 3. So that becomes x squared over 2. And then if I integrate 2, remember I have to use rule 1 because I take the coefficient out, and this is going to be 2x, and then plus c. So that's what y equals. So just like before, we have to find the y value, and let me zoom this out in a little bit. We have to find the c value when x equals 0 and y equals 1. Okay, so again, I have to find c. Okay, so I'm going to plug in all this information. So y equals 1. We have 3 halves e raised to the 2 times 0, which will 0 out, plus 1 half times 0 squared, plus 2 times 0 plus c. All right, so basically, and I'm going to need a little bit more room, so if you need to pause me right now, pause me, because I'm going to rewrite this out and solve the rest on this page. All right, so we're at this point here, and I'm going to erase this bottom half because I just wanted to rewrite it, where we were plugging in x equals 0 and y equals 1 into the original function. So I need to just plug in for y. So once again, y equals 1. So let me go ahead and do that. So this looks like this. 1 equals 3 halves times e to the 0, which is 1. And then I have plus 1 half times 0, which is 0's out. And then I have 0 times 2, which is 0 plus c. So I get 1 equals 3 halves plus c. So if I find a common denominator, I have 2 over 2 for 1. And then I'm going to subtract 3 halves. That's going to give me my c value. So c equals negative 1 half. Okay, so finalizing the problem, my function is going to be 3 halves. That was wild. Let's try that again. 3 halves e to the 2x plus 1 half x squared. I do not know what is going on with this pencil, but it's making it very hard to write. but I'm going to do that again. 1/2 x squared plus 2x, and then minus c, which is now negative 1/2. So that's going to be my answer. All right, so example 8 is finished. Now let's go on to the last example of this section. All right, so we're going to look at applications of differential equations, and in particular, we're going to look at rectilinear motion. So before, we learned if we took the derivative of the position formula, or s at t, we got the derivative of s would give me the velocity formula. And if I took the derivative of the velocity formula, that equaled acceleration. So with antiderivatives, we can work backwards. So for instance, if I start with the acceleration function, if I integrate acceleration, I get velocity. And if I integrate velocity, then I get back to the standard position. So if I look at example number 9, it says a projectile is fired vertically upwards from the top of a 100-foot building with the initial velocity of 50 feet per second. Okay, I know this is an initial velocity formula because I'm given an initial velocity of 50 feet per second. I also know that the height of the building is 100 feet. Okay, so the question is, when will it hit the ground? So if I want to know when it's going to hit the ground, I basically want to know time. And to get time, I'm going to have to find the position function. So I'm going to have to look for s at t. Okay, so if you look at this, I'm not given too much information. I do have an initial velocity of 50 feet per second when time is 0. And I also have a little note here that the acceleration of gravity equals negative 9.8 meters per second squared, or 32 feet per second squared. So before we use this do this problem, you got to understand that acceleration is usually feet or whatever per second or whatever time squared. Velocity would be feet per second. And then time, if we plug in the time formula, we should get height, right? Or feet. Okay, so that's how you can tell like what you're given and where you're starting. So on the next page, I have the same problem, but I just wanted more room. So I'm going to start with what I'm given. I know the acceleration at time t is given to me. It's negative 32 feet per second squared. And I got that from right here, okay? All right, so I'm at the acceleration. If I want to get velocity, I have to integrate the acceleration formula. Okay, so if I integrate the acceleration formula, that's going to give me velocity. Okay, so let's do that. Let's integrate negative 32 feet per second squared. Okay, so if I want to integrate negative 32, I'm going to use rule number 1. So basically, when I integrate that, I'm going to get negative 32, in this case, t. Okay. All right. Plus my constant in terms of velocity. Okay. So that's what my function is. So v at t equals negative 32 t plus the constant of velocity. Now, I know my initial velocity is 50 feet per second. Okay, so I can plug that in and figure out what we have here. right? So if the initial velocity is 50 feet per second, I can plug in 50 and for v at t because I'm looking for c. Remember, we have to find this before we move on to finding the standard or the position function. All right, so we have 50 equals negative 32. Now the time is 0. And the reason why I'm saying that is because that's the time it starts, right? Plus CV. So once again, we're looking for that constant of velocity. I plugged in the time equals 0 and v at t equals 50, and I got that from the initial problem. Okay, so when I solve that, I get 50 equals 0 plus CV. So the constant of velocity equals 50, which we expected that because that's what they told us it was actually. All right, so the velocity function officially is going to be negative 32t plus 50. Okay? So I have to integrate that again because it wants to know when will it hit the ground or what's the time, right? So if I integrate the velocity function in terms of t, I am going to get the position function. Okay? So I'm going to do that. I'm going to integrate negative 32t plus 50 dt. Okay, so once again, we can break this up into pieces. If I take the negative 32, factor it out, I'm going to integrate t, which, by the way, I'm going to use rule 3, plus I'm going to also integrate the 50, which is, you can do this, 50 times 1 dt if you want to be proper. And I'm trying to write in dt, but it doesn't look like that. Okay. All right, so when I apply these rules, I get negative 32t squared, right? Because I have to add 1 to the t, and remember that I have to divide it over 2. And then the integration of 1 is rule number 1. So that's x, or t in this case. So we got 50t, and then plus c, okay? So the standard position function is negative 16, and I got that by taking negative 32 divided by 2, t squared plus 50t, and then plus the constant. And this time around, we're using the position function, so I'm going to put constant at s. Okay. All right, guys. So remember, s at t is the height at the initial. All right, so when we plug these in to find c, we're going to let the height of this be 100. And then the time again is 0 because this is the time it starts. Okay, so once again, how did I get these values? I got them from the original problem, 100-foot building. So that's s at t. So given s at t equals 100, and we know the time is 0. Okay, so let's go ahead and crunch some numbers. I know everything's going to 0 out, so basically 100 is going to be my constant. So let's write this up. S at t equals negative 16t squared plus 50t, and now instead of writing c, I write 100. Okay, so the question, to answer our question, it's what's the time? When does it hit the ground? Okay, so if it's going to hit the ground, okay, wouldn't you guys agree that the height has to be 0? Okay, so what I'm going to do is I'm going to take that function and set it equal to 0 and solve. Okay, so let's go ahead and do that. We're going to take that function, s at t, set it equal to 0 and solve. So s at t is 0, because remember that's the height. So I get 0 equals negative 16 t squared plus 50t plus 100. Okay, I'm looking at that, and I don't think it's going to factor out too nice, so we're going to have to use a quadratic formula. So quadratic formula, just as a reminder, is negative b plus or minus the square root of b squared minus 4ac all over 2a. And that'll give me my roots or my x values. Okay, in this case we're doing t. So negative b is going to be negative 50 plus or minus the square root of 50 squared minus 4 times a, which is negative 16, times c, which is 100, all over 2 times a, which is negative 16. Okay, so if you plug all this in, it's going to look like this. T equals negative 50 plus or minus the square root of no, but anyways, I'm just going to plug this into my calculator, make things a little bit faster. And when I plug this into my calculator, I'm going to get two values. I'm going to get positive 4.51, and I'm also going to get a negative value, which is negative 1.386. This value doesn't make sense because remember, we're looking for time. Okay, so we can't have negative time. So we're going to disregard this guy, but we're going to accept this one. So the time it hits the ground is approximately 4.51, and we're in seconds, because remember, it was given feet per second squared. Okay, so just to overview this problem quickly, we started with the acceleration, and how did I know that? Because my units were in feet per second squared. I took the integration of acceleration to get my velocity function. At that point, I used to find c, the 50 feet per second, because that was the initial velocity that was told to us in the original problem, to find the velocity formula. And then I took and integrated the velocity formula to find the position formula. At that point, I plugged in 100 to find c, and after I found c, I then plugged in 0 for s at t, because s at t is the height, because when it hits the ground, the height is 0. I used quadratic formula to then figure out what the time was. And that's the end of this section, so that's it, and I know you guys have to watch the next section as well. So that'll be it for today.